Now, when I look at that list of potentials, as I look down through there, most of the time we'll find that these are ordered typically from high to low. And if you take a look at things that are really, really low, we see things like lithium ion going to lithium with a 0 charge, or sodium ion going to sodium with a 0 charge. And when I say low, -3, -2.7, we see values such as those. Now, we look on the side for higher values, positive values. I see things like silver ion +1 with a relatively high value. Gold 3 going to gold solid, a relatively high value there. Definitely some other things that are even higher values than those, but we start to see things that are lower on our activity series. The neat thing about it, when we do reduction potentials, and if we look at them from highest to lowest, it's actually our activity series of our metals and some nonmetals and some acid-base redox reactions, and they're just simply flipped upside down. So this gives us the activity series of the metals as well, simply by looking at this chart. When I go back to this reaction that I have here, I've got the silver being reduced, and I'm looking for a value for that, and I'm looking here in the back of a chemistry book for these values, and the value it gives me for that is 0.8. Now again, that's for 1 Ag plus 1 electron to 1 Ag solid, but again, the 2 doesn't change anything. It's 0.80 volts. On the other hand, if I look for zinc going to zinc 2, I'm not going to find it because that's oxidation, so I've got to find the opposite of that, zinc 2 plus 2 electrons, and that one has a value of -0.76. Now again, negative for the reverse of this reaction, but I'm going to change that sign from -0.76 to +0.76 because this one is oxidized. To get the total EMF, I simply just add those up. 1.56 volts is the cell potential, or the cell electromotive force, or the cell voltage, if you want to call it that. You look through that list and you see things. If you look kind of toward the middle of the list, you'll find that there is one thing listed on there that has a value of 0. And that value of 0 is 2H plus 2 electrons going to H2 gas. For instance, if we place zinc in hydrochloric acid, we would get a net ionic equation that looks something like this. So if I were to calculate a voltage for this, I would have my H2, or my 2H pluses going to H2 being reduced, my zinc being oxidized, but the value for this reduction potential here is 0. And the reason why, we call that a standard hydrogen electrode. And what that means is this whole entire chart is based on how everything compares to a reaction in something like a strong acid, some source of H plus to generate H2 gas. We need a standard by which everything else is measured. So when we say that the value for silver being reduced from a 1 to a 0 charge is 0.8, we're saying in comparison to the standard hydrogen electrode, it's 0.8. But the good news is, it doesn't matter as long as we keep the standard the same by which all of these are compared, then we're going to get the same value. We could have used a standard zinc electrode, and when you add up the values in the end, you're still going to get the exact same total when you add them up. So the reason why the value for this here is 0 is because our reduction potentials are defined based upon something called a standard hydrogen electrode. Is a quick way to kind of represent that same reaction that we had there a moment ago. Again, zinc plus 2 Ag plus, zinc plus 2 Ag, and we do it this way. We say Zn to Zn plus plus, 2 lines, 2 Ag plus, single line, to 2 Ag. This is called a shorthand representation of a cell, and this is the side that's being oxidized. You can kind of think of this as being the salt bridge, the divider in the middle that separates the oxidation from the reduction, or this is my anode alphabetically, and this is what's going on in the cathode cell here on the other side. So this is called a shorthand representation or a cell representation, and all we're doing is we're taking what is oxidized, separating it with a single line, taking what is reduced, single line, and then separating the two with double lines there in the middle. So that's the shorthand representation of a cell. So if I gave you copper and said, okay, you've got copper and copper 2 nitrate, and you've got zinc and zinc nitrate, 1 molar solutions of the 2 nitrates, and a piece of copper and a piece of zinc, and I said, okay, take that and draw a full entire galvanic cell showing everything that I just went through, as well as, instead of putting a light bulb up at the top, put a voltmeter and write in what that cell EMF would be. This would be a great place to pause the video. I'm going to post the answer here in just a second, but you got to start by determining the spontaneous reaction. So I'm going to post the answer, and again, you should probably pause it at this point and go ahead and give it a try on your own. So I'm going to run through the answer to that question. So my spontaneous reaction is here at the bottom. How do I know that? Well, there's a couple ways I know that. One is I know my metal reactivity series, and I know that zinc is more reactive than copper, so it'll displace copper away, thereby reducing the copper, and my zinc will be oxidized. And here is that oxidation half reaction and the reduction half reaction. But there's another way that I know in electrochemistry that I've done this problem correctly. When I add up this voltage, if I get a positive voltage, I know that I have a spontaneous reaction. So that's always a good sign. If you get to the end, you get a negative voltage, you've probably done everything completely backward. Again, 1.10 volts because I looked up the reduction potential. The oxidation potential, not listed, but the reduction potential was negative 0.76 for the zinc, so therefore just drop the negative sign. Again, no coefficients here to worry about, but had I doubled anything in electrochemistry, double the moles, don't change the voltage. The only time you change anything is you change the sign for the one that is oxidized. And what would that cell look like? Well, up top I've got my copper in my copper 2 nitrate solution. I've got my zinc over here in my zinc nitrate solution. The electrons are going to be produced, I see that here, by the zinc going to the copper. So I drew that arrow in, and then to me that makes it real easy to go ahead and put the anions going opposite through the salt bridge, kind of maintaining that negative part of the loop. If anions are going this way, then my cations are going to migrate to the right. In order for this to happen with zinc, this electrode here is going to break down, the mass is going to decrease on the zinc, and the copper, it's going to plate on this copper electrode. The copper is going to leave solution. As a matter of fact, not only would I see the zinc breaking down and the copper plating, but this solution here being a blue solution, it's going to change. It's going to become fainter as more and more of that copper plates, meaning that molarity is going to change once this thing starts to operate. Up top here, I've got this drawn connected to a voltmeter with 1.10 volts, the cell EMF for that. Started this video off, talking about just basic single displacement and redox reactions, and I took you through how we turn that into an electrochemical cell. And when I made that transition, when we started calculating cell EMF, I said, okay, this is maybe more of a second-year chemistry. So now this final part, this is definitely second-year chemistry, AP chemistry type calculations, college chemistry calculations. So the final segment of this, I'm going to run through just some difficult calculations and questions. So I give you this question, and I might say, justify whether or not this is a spontaneous reaction. So in order to do that, if you have those reduction potentials, you can look those up. And we're going to go with Cu++ plus 2 electrons to Cu. When I look up the reduction value for that, I get 0.34 volts. On the other hand, Fe to Fe++, iron 2, not iron 3, plus 2 electrons there. Again, I won't find that value because that's oxidation, but I can find the value for the reduction of that. And that reduction value is negative 0.44, so I'm going to change that, or sorry, that reduction value, yes, is negative 0.44, so I'm going to change that to positive 0.44 volts, and when I add those up, I end up with 0.78 volts. So I could answer the question this way. I could say, yeah, this is spontaneous because it's got a positive cell EMF. But now, this is kind of where everything kind of crashes in together, because that word spontaneous takes us back to another way to determine if a reaction is spontaneous, and that's by the Gibbs free energy. And I'm not going to go through deriving this equation, but I do need you to be able to calculate this. You can find delta G for a reaction by doing negative N F E, where this is your cell potential, your cell EMF, your cell voltage, whatever you want to call that. This is Faraday's constant. And we'll talk about Faraday's constant here and where it comes from. It is 98,485. Some books use 98,500. And that's coulombs per mole of electrons. And N is mole of electrons. Now, I'll explain where all of this comes from and why this equation works out the way that it does as we run through this. So we get equals negative, we'll start there, N, moles of electrons. When we balance those half reactions, that's part of the reason why we have to be able to do that. We need those moles of electrons. And there are 2 in this particular reaction. Faraday's constant is the coulomb to mole ratio. Now, a little while ago, I gave you the coulomb to electron and the electron to mole ratio, and we can actually combine these, and that's what Michael Faraday did, is he actually combined these terms, and he came up with a coulomb per mole of electron ratio, and that's where that value comes from. So there's 98,485 coulombs in every mole of electrons. 98,485. And then lastly, our cell EMF, 0.78. Now, why would we use a cell EMF? Well, we've got moles of electrons times coulombs per mole, so the moles are going to cancel. And remember, voltage is joules per coulomb, so when we multiply those out, the coulombs are going to cancel, and that's going to give me an answer here that's going to be in joules. So when I plug those in and I solve, I end up with negative 1.5 times 10 to the 5th joules, or we could convert that over to kilojoules. Now again, delta G here is negative. Why? Well, it's pretty simple. We got a negative sign here. This is moles of electrons. It's a positive value. This is a constant. It's positive. If this is positive, then delta G is going to be negative. So understand that positive EMF, spontaneous, negative, delta G also tells us that this reaction will be spontaneous.